I would like to thank the organizer for inviting me to this interesting event. Today, I will present our current activity on carbon nanostructures for energy storage application. So, okay, good. Okay. The nanocarbon laboratory operates in Parma, Italy, at the Department of Mathematical, Physical, and Computer Science in the university campus. Since more than 25 years, has dealt with the synthesis and the physical characterization of novel carbon nanostructures, mainly fullerenes and graphene-related compounds. Here you can see a recent picture of my research group. I would like to take the opportunity to acknowledge all of them. Can you see the presentation? Sorry, I cannot see the, it's not clear if you can see the presentation is going on or no? Okay, good. Now I see. Good. As I told you, our research is focused on carbon-based nanostructures. We have a carbon nanostructure whenever at least one of its physical dimension is reduced at nanometer scale. The most famous carbon nanomaterials are two-dimensional graphene, the only one-atom T-carbon sheet, one-dimensional carbon nanotubes obtained wrapping graphene sheets, and zero-dimensional fullerene molecules obtained curving the graphene sheets to obtain a closed surface. The nanocarbon laboratory research activity ranges from the study of high temperature superconductivity of carbon nanomaterials to the investigation of their interaction with hydrogen for solid-state hydrogen storage application. Again, from the synthesis of novel active materials for ionic batteries to the employment of porous carbons for supercapacitor electrodes to the investigation of the physical properties of carbon nanomaterials in composites. Here we focus on some selected examples of novel carbon nanostructures produced in the nanocarbon laboratory suitable for energy storage purposes. The theorization of an hydrogen economy dates back to the 70s as a possible solution to the progressive fossil fuel depletion, the consequent environment pollution, and the need to reduce greenhouse gas emissions, which are cause of the climate change. In fact, hydrogen is abundant in nature, although only a small fraction is directly available. For example, it can be easily produced water hydrolysis, exploiting the energy provided by energy. Its combustion does not produce greenhouse gases and is highly energetic. In fact, hydrogen delivers 3 times the energy of fossil fuels. For this reason, it's considered an excellent energy vector rather than a fuel. The main limiting factor to the development of an hydrogen economy, however, is due to the still inefficient storage of this gas. The most common strategies adopted so far are represented by physical storage, namely compression and liquefaction at very low temperature, but both of them faced with severe technological problems and still too low storage efficiency. The scientific community agreed that the best way to store hydrogen is solid-state absorption. Basically, hydrogen is physically or chemically bound in a compound with the right energy and in a reversible way. So far, many compounds have been isolated with good hydrogen storage properties, but none of them still meet all the strict requirements of the US Department of Energy, and they are far to compete with the performance of a common gasoline tank. If we focus on carbon nanostructures, they are able to store significant amount of hydrogen, but the binding energy, depending on the storage mechanism considered, is too low or too high for practical applications. In the first case, hydrogen is weakly bound to a porous carbon network with a physisorption mechanism with typical binding energy of the order of few kilojoules per mole of H2. The physisorption process needs rather low operating temperature, below 100 K, unsuitable for application. In the second case, hydrogen can be strongly bound to the carbon network via chemical sorption mechanism, as for example in hydrocarbons. In this case, the energy required to release hydrogen is too high, of the order of 100 kilojoules per mole, hence it's still impractical. Hence, it's necessary to tune the binding energy in the suitable range of 20-50 kJ per mole to have hydrogen absorption desorption close to room temperature. And it was theoretically proposed that there could exist several strategies to reach this target. In particular, in case of carbon systems, it has been proposed that besides more exotic strategies difficult to realize, it can be obtained simply by both curving the graphene plane and charging the curved carbon. As I told you before, fullerenes are class of nanometer-sized carbon molecules obtained curving the graphene plane by replacing hexagons with pentagons. The most common fullerene molecule is C60, containing exactly 60 atoms of covalently bonded carbons and is shaped like a nanoscale soccer ball. If exposed to high temperature and high pressure hydrogen treatment, C60 gets hydrogenated and can covalently absorb a rather large amount of hydrogen. Unfortunately, this process can be reached at quite extreme condition, and it is irreversible, as the hydrogen release is followed by fullerene cage collapse. Nevertheless, the chemistry of C60 fullerene is quite rich. And for example, it is well known that C60 can form the so-called alkali intercalated fullerides, which are actually charge transfer salts, where the alkali ions donate an electron to the fullerene molecules, thus populating the LUMO band and negatively charging the cage. In particular, we managed to isolate some alkali cluster intercalated fullerides, where alkali ions form small clusters inside the octahedral voids of the crystal, which turn out to be able to absorb up to 6% of hydrogen at moderate pressure and temperature condition, and very importantly, in a reversible way. The hydrogenation mechanism of this alkali cluster intercalated fullerides has been investigated by means of in situ high flux neutron power diffraction, which is displayed in this picture for the case of lithium 6060. The diffraction pattern collected every minute during the hydrogenation process show the progressive expansion of the fullerene lattice upon heating, indicating the C60 hydrogenation, followed by a side reaction of lithium clusters with hydrogen and the subsequent formation of segregated lithium hydride, in this case lithium deuteride. It's worth noting that in this and the formation of the hydride happen at much milder condition with respect to what observed in the case of pure C60 and pure lithium hydride respectively. Moreover, in this case, the process appeared fully reversible, and after a thermal cycle, it was possible to recover the initial compound. In order to gain further information, such materials have been investigated with muon spin resonance, a peculiar and exotic technique consisting in the implantation of polarized positive muons in the sample and in the study of the precession of the muon spin as a function of time. This can be done since muons decay with the half-time of few microseconds, emitting a positron in the direction of the spin. Positive muons chemically interact with the electrons of the carbon backbone and form muonium, which is a light isotope of hydrogen. Hence, a mu-SR experiment is equivalent of implanting a single hydrogen atom in the sample and following its behavior by measuring the muon spin evolution. In the presence of hydrogen molecules, in our case, mu-SR allows us to understand that atomic hydrogen absorption already occurs at very low temperature in the fullerene molecules. And in presence of hydrogen molecules, the dissociation process is mediated by the alkali clusters, whose limiting factor is represented by the still relatively high dissociation temperature. This process can be, for example, catalyzed by adding small amount of platinum or palladium nanoparticles. And in fact, in this case, we managed to further increase and optimize the hydrogenation of the materials, meeting the DOE target. Let me conclude this part by showing you, that relevant amount of reversible hydrogen in these systems can be also obtained indirectly by the absorption and desorption of a nitrogen carrier, which is ammonia. We found that the interaction of lithium cluster intercalated fullerized with liquid ammonia bring to the formation of novel metastable ammonia co-intercalated lithium fullerides, which are stable near room temperature. By heating the sample, we managed to follow two-phase transition starting from the perammoniated precursor, respectively at 80 and 260 centigrade degrees, which we studied by means of in situ high flux power neutron diffraction and differential scanning calorimetry. The overall release of ammonia in these compounds exceeded 30 weight% of ammonia, corresponding to rough 5.5 weight% of hydrogen, which is quite an amount of hydrogen, and the process also in this case is reversible. We can conclude that we managed to identify a novel class of reversible hydrogen absorbers able to meet the stringent requirements of gravimetric capacity, where the main limitation in this case, however, is now represented by the cost of the raw materials, in particular the cost of fullerenes. We are currently investigating less expensive carbon nanostructure displaying a similar hydrogenation mechanism and comparable performance. Let me now switch to another topic concerning our research on carbon nanostructure as active materials in electrochemical energy storage systems, in particular ionic batteries and supercapacitors. As you probably well know, lithium-ion batteries represent the state of the art in terms of electrochemical energy storage. Basically, they are composed by three components: a positive electrode, a negative electrode, and a separated socket by the electrolyte. The first two are lithium intercalation compounds, while the electrolyte is a good ion conductor, but a bad electronic conductor. During the discharge process, lithium migrates from anode to the cathode, allowing the electronic flux to the device connected to the battery. Lithium-ion batteries are a secondary battery, namely rechargeable battery. Hence, the process can be reversed during the charge, which replaces the initial state of the battery, and this can be done many times. Nowadays, lithium-ion batteries are extensively employed as power supplies in small electronic devices, but there is an enormous interest to extend their use to large-scale applications, such as smart energy grid and automotive application, for example. This fact would, however, cause several problems because of the relative scarcity of lithium in nature, as we can see from this periodic table drawn accordingly to the relative abundance of the elements. Lithium is very small. Furthermore, lithium reserves are unevenly distributed and are found in few countries in the world, making it difficult to supply. A possible solution could be switch from lithium to sodium and consider the novel sodium-ion batteries. In fact, sodium is much more available in nature and less expensive than lithium, while keeping the same chemistry, more or less, thus allowing to recover part of the lithium-ion technology. On the other hand, performance of sodium-ion battery is expected to be slightly worse than lithium-ion battery due to the dimension of sodium-ion, which is larger than lithium-ion. On the other hand, another point, another weak point, is that sodium does not intercalate in common lithium anodes, such as graphite and silicon, and this requires some research on material. In our laboratory, we produce gram scale of graphene-based materials by means of thermal exfoliation of graphite oxide. In more detail, we start from graphite oxide, obtained by treating graphite with strong acids and oxidants, and we expose it to a thermal shock at very high temperature in a controlled atmosphere. The exfoliation process is promoted by the quick release of the functional groups covalently attached to the graphene sheets. The obtained product contains a large fraction of single and few layer graphene nanoplatelets, displays a pretty high specific surface area, and good electric conductivity, and also quite a large amount of defects. TIGO can also undergo further functionalization steps, for example, high temperature hydrogen treatments. This process can lead to the partial saturation of the in-plane defects, such as edges and carbon vacancies produced during the exfoliation process. Alternately, TIGO can be decorated with small metal or metal oxide nanoparticles, such as nickel, platinum, copper, titanium oxide, for example. In this picture, we can see the synthesis route of nickel TIGO, in which around 20 nanometer diameter of nickel nanoparticles are drawn on graphene sheets via the wet impregnator of a metal organic precursor, followed by the evaporation of the solvent and the neat treatment in vacuum. TIGO-based materials have been employed as negative electrodes in lithium and sodium research coin cells and probed with electrochemical measurements for several cycles. We found that whenever the graphene plane's exfoliation occurs, differently from graphite, graphene compounds can easily and reversibly intercalate large amount of sodium ions. And the performance improves when TIGO is functionalized with hydrogen, the red curve, and the nickel nanoparticle, the blue curve in this case, reaching up to 600 milliampere hour over gram capacity at 100 milliampere hour over gram rate of charge. As a comparison, the performance of standard graphite anode materials in lithium-ion batteries is reported here. And we can see that also that the peculiar voltage versus capacity slopes in graphene suggest the presence of capacitive charge storage mechanism associated to the intercalation, which would explain the high rate capability of TIGO-based electrodes. The sodium intercalation mechanism in TIGO-based electrodes has been investigated also with the NMR measurements in magic angle-spinning configuration on the sodium nuclei, performed on ex situ on differently cycled electrodes. The spectra show the presence of either mobile or immobile sites ascribed to sodium ion, which are intercalated or deintercalated during the battery discharge or charging. And on the other hand, the sodium ion trapped in the solid electrolyte interface. Further electrochemical characterizations, such as impedance spectroscopy and 3-electrode cyclic voltammetry, allowed us to better clarify the presence of two intercalation mechanisms for mobile lithium and sodium in graphene. A battery-like electrochemical intercalation due to lithium insertion between graphene layers and responsible of the large capacity of graphene, and an electrostatic accumulation of charges due to lithium absorbed into the graphene pores or attracted by electrical charges on the graphene surface, responsible of fast charge and discharge capabilities. In the last part of the talk, I will focus on a different class of emerging energy storage devices, so-called supercapacitors, which bridge the gap between batteries and conventional capacitors in terms of energy and power they can accumulate. We should further distinguish among this class of devices between electrical double-layer capacitors, so-called ADLC, where the charge is accumulated via a completely physical process, and pseudocapacitors, where fast surface redox reaction occurs. And while the formers allow very fast charge discharge and almost infinite lifetime, the latter can store more energy, although still lower than batteries, but which with low lifetime than EDLC. And in our lab, we are developing a novel method to produce graphene based on the laser photochemical conversion of suitable precursor. It has been demonstrated, in fact, that it's possible to convert several plastics, such as polyimide in graphene, using an infrared CO2 laser, or even convert graphite oxide in graphene exploiting the cost-effective laser or DVD writer. In both cases, interdigitated graphene electrodes devices can be easily realized in a scalable way and very quickly for a wide spread of particle application ranging from sensing to energy storage. And in particular, we manage to produce laser-striped graphene decorated with titanium dioxide nanoparticles by means of one-pot photothermal conversion of a precursor containing an aqueous solution of both graphite oxide, which is the precursor of graphene, and titanium isopropoxide, which was the precursor of titanium dioxide nanoparticles. And the successful graphene decoration with titanium nanoparticles, mainly in artase form, has been confirmed by transmission electron microscopy. We can see in this picture, but also via Raman spectroscopy, X-ray diffraction, XPS spectroscopy. The interdigitated symmetrical supercapacitor has been assembled following a standard protocol displayed in this picture. And the devices were tested with a cyclic voltammetry and galvanostatic charge discharge measurements. And we found that the presence of titanium dioxide nanoparticles almost doubled the capacitance of the devices, thanks to the presence of paradic effects on the titanium nanoparticle surfaces, reaching the noticeable specific areal energy of 0.22 microwatt hour over square centimeter. And also the capacitance retention in these systems seems to improve as compared with bare graphene systems, as observed by testing the devices for over 3,000 cycles. So to conclude, a selection of novel carbon nanostructures for different energy storage applications has been presented, and among them, I show you that alkali cluster integrated fullerenes represent a new promising class of solid-state hydrogen absorbers. And from the side of the electrochemical storage, we found that bulk graphene produced via thermal exfoliation of graphite oxide behaves as a good negative electrode for both lithium and sodium-ion batteries. The sodium-ion batteries are much more innovative systems than lithium-ion batteries. And eventually, laser-striped graphene, either pristine or decorated with metal oxide nanoparticles, turn out to be an efficient port electro-inflexible interdigitated microsupercapacitors. I would like to thank all of my collaborators and would like also thank you for your kind attention. And for any information, please refer to my contacts in the box. Thank you so much.